Okay, this is Sir Isaac with Miss B, part 2. Today we're going to be talking about net force and force components. As you can see, you will need a ruler or straight edge in order to draw these out into your notes. And please, as you're going, be exact, be careful, and draw the components to the exact lengths, and of course label everything. But I'm going to keep this one pretty brief. I think it's an easy concept for us to talk about because we've had, talked about components with vectors already. But with forces, obviously Newton's second law says that if there's a force acting on an object, it will cause it to accelerate. So in order for an object to remain at rest or to remain in a constant velocity, that is to not accelerate, then the sum of all of the forces must add up to be 0. And again, this is our symbol for sum of, it's sigma F. So the sum of all forces, or the net force, must be 0. It's easy if we are talking about this in only one dimension. So here's a guy being pulled, F1 and F2 in different directions, and all of this is happening in, let's say, the X. That's what it looks like to us. Of course, we don't want any outside forces, so maybe we have a hypothetical frictional skateboard that we've added to him. And so one person's pulling in one direction, another person's pulling in the other direction. We could make that 50 newtons apiece. And of course, now the net force, the sum of all forces, would be 0 because they are in opposite directions. So we subtract them. 50 minus 50. Excellent. Or maybe instead of 50 newtons and 50, we have 50 newtons and 10. Now the net force would be to the left, or his right, our left as we look at it, with a force of 40 newtons. So 50 minus 10, we could draw that out. Again, that's the net force. That's a little bit easier because it's only in one dimension. We want to step into any force in any direction, and we can also solve that. It just means we have to remember that a force in a direction is actually a resultant, that is the sum of all of the components that it's made up of. And in true form, that would be in all three directions. So F1 is actually a vector that's made up of F1 in the X component, the F1Y component, and F1Z component. For the sake of ease right now, we're only going to be looking at X and Y. We don't have a Z component in this at all, but that is how we'd solve them. Which means if we want to solve the net force between F1 and F2, we can break it down into its components and solve for the sum of each of those. So the net force is the sum of all the forces in the X, the sum of all the Y components, and the sum of all the Z components. Or in other words, you're going to want to take your time drawing this out, but I'm going to go through it pretty quickly so you can pause as you need. But F1 broken down into its Y component and X component. F2, again, we can break it down into its X component and its Y component. That is how much of it is going in the X and in what direction, how much of it is going in the Y and in what direction. And we can say, well, pictorially, we could have just added these F1 and F2 by moving F1 down to, so it's head to tail. And now the net force, sorry, that symbol is not right, but that's sigma F. The net force is the sum of F1 and F2 as we've moved them. We can do the same thing, though, by adding up the component vectors. So let's move the F2x. So now we have both of the X components added head to tail. And we can take F1y and F2y, that is the Y components, and they're going in opposite directions, so we subtract them. Their net force, so the net Fy is what I've just drawn in over there to the right, which would make the resultant from the beginning to the end that same, exact same sum vector that we have when we did it the first way. So what we're seeing here is that you can actually find the sum of all the forces by adding the sum of all the components. Okay. And that's, of course, just the original way. Here's another example in just one dimension. So if Fx is 0, that is the sum of all forces in Fx is 0, so there's none shown here. And the sum of all the forces, the net force in the Y, is 10 pounds plus 10, which equals 20. Now, it would be, of course, moving. That's the net force. It would be moving upward based on the mass. We don't know the mass. We can't find the acceleration, but it would be moving. So let's say that this is a static system, though, which would make us wonder how much force F do we need to keep it static And obviously that would be 20 pounds because we need to counter the 20 that's coming upward. Okay, I want you to try this one. This is actually going to be on your quiz. It's what I wanted to make sure that you understand it. I'm going to take you through most of it, but let's say you have a few forces acting on this box. So you have a 10 Newton force at a 45-degree angle, a 10 Newton force, and a 15 Newton force at a 30-degree angle, all as labeled or as shown. What is the net force in the X? Because again, that's how we're going to solve these, is break it down into its components and solve net force in the X, net force in the Y, and then you can add those together, Pythagorean theorem, to actually solve for the total force that's acting on the box. And if we know the total force, then of course we can also find acceleration because we know it has a mass of 10 kilograms as listed there. Okay, first thing you need to do then is break it down. In the X direction we have 10 newtons right there. So that is a 10 Newton force. It's already in the X, so it doesn't have any components. We also want to break down the components of each of these. So let's do the 15 Newton one first. In the X, there's a component of it right here that is the 15 newtons times the sine, so the sine of 30 degrees times 15 newtons. And there's an X component of the 10 newtons. Of course, this one is going to the right. So we have a 7.5 to the left, and we have this X component of the 10 Newton force over here, which would be sine of 45, or excuse me, cosine of 45 degrees, because a different angle is given, times 10 newtons, which equals 7.07 newtons. A little off the sig figs, of course, that would be 7.1 when we get our sig figs in. This is now a total force of 10 to the left plus 7.5 to the left minus 7.1 to the right. So the net force with sig figs would be 10.4 newtons. In the y direction, now we have no component of this one, but down here we have a component of the 15 Newton, which is now the cosine of 30, because it's the adjacent to the angle, times 15 newtons, which you can plug into your calculator. You get 13. And the sine, because now it's opposite of the angle, that is this vector right there. So that's the y component of that vector. And it is sine of 45 times 10 newtons, and it equals again 7.1, which is, sine of 45, same as cosine of 45. And this time both of those are acting up, which means we have a net force of the 13 plus the 7.1 together, 20 point, to give us our sig figs, which means we have a force up of 20, a force to the left of 10.4. Use Pythagorean's theorem, find the angle, and you will get the net force. I'm going to leave that for you as your homework. I also put a Mythbusters video on with them testing the car crashes, so take a look at that, and we're going to discuss it on Monday. All right, have a great weekend.